So in the last section in Chapter 9, this is 9.3, we're looking at limiting reactants and calculating percent yields. So two words we need to define. Limiting reactant, which is defined right here, says the reactant that limits the amount of the other reactants that can combine and the amount of products that can form. So it gets used up. So I like to think of a limiting reactant as a reactant that gets used up. The one that doesn't get used up is an excess. It's left over after the reaction. Pieces left over, those are called excess. So we can think about it this way. Imagine we were trying to build a bicycle. A bicycle takes these pieces. You need a frame and you need two wheels. Well, if you have a third wheel, you can't build another bicycle. You need to have a pair of wheels. Even if you have a pair of wheels, we can't build yet another bicycle. We would also have to have a second frame. So in this reaction, if we had, let's erase that frame. If we had, well, let's do it. So that is my best attempt at drawing a second frame. So here we go. We have two frames, but we only have two bicycles. And we'll say, well, how many bicycles can we build? Well, we can only build one, because we only have wheels enough to build one. So my frame would be an excess. My wheels, in this case, would limit the reaction. Well, maybe we should look at it with real atoms here. So we have 5 carbon atoms. So we have carbon. And we're burning it in the presence of oxygen. So we have 5 carbon atoms, we have 10 oxygen molecules. Well, when those react, that will make 5 carbon dioxide molecules. So if we burn that carbon in oxygen, we can make 5 carbon dioxide molecules. Now, notice, in this case, 10 times 2, we have 20 total atoms of oxygen. They don't all get used up. They don't all get used up, because each carbon can only bond to 2 oxygens. So notice a total of 10 oxygen atoms were used. So there's 5 molecules in excess. They're left over. So we have excess oxygen in this case and limiting amount of carbon atoms. But maybe it's easier if we actually do the calculations with these. So instead of looking at bicycles and balls, let's see if we can actually do a calculation. So I'm going to do this first one, and these are the section reviews from your book. It says carbon disulfide burns an oxygen to yield carbon dioxide and sulfur dioxide according to the equation as listed. If we have 1 mole of carbon disulfide, so I'm going to write that down, 1 mole of carbon disulfide. So anytime it tells me an amount I have, I'm going to write it down, and it's combined with 1 mole of oxygen. Now it says identify the limiting reactant. Here's how I'm going to do this. I'm going to convert both of these into a uniform product. So I can't compare them next to each other. I'm going to compare them to a uniform product. And I'm just going to pick the CO2. I could do the sulfur dioxide. I'm just going to convert both of these into CO2. So 1 mole of oxygen, if I look at the ratio, 3 oxygens are needed to produce 1 CO2. So 3 moles of oxygen produce 1 mole of CO2. So there's where I'm just putting in the mole ratio. Now if I look at my carbon sulfide, 1 carbon sulfide produces 1 carbon dioxide. So my ratio here is 1, it's supposed to be 1 mole of carbon disulfide reacts to produce 1 mole of carbon dioxide. Now if we take a look at that, and I erase my mess here, I solve these both. Well, notice carbon disulfide cancels. In this one, oxygen cancels. This one, I make 1 mole of carbon dioxide. In this one, notice I have 1 over 3. I make 0.33 moles of carbon dioxide. Okay, so here's the question. How much do I actually make? Well, I always make the less amount. This is saying I could make 1 mole of carbon dioxide if I had 1 mole of carbon disulfide, but I don't have enough oxygen to react. So always we pick the less one. This is the amount I'll actually make. This is called my theoretical yield. And this over here then would be my limiting reactant. So oxygen is limiting, carbon disulfide is in excess, and 0.3 moles of carbon dioxide would be my theoretical yield. So we always have to take both of the reactants that they give us, solve them both for one common product, and then compare them. Whichever less, that's our theoretical yield. It is made by the limiting reactant. So that means this is all going to be used up, and we're going to have no more oxygen, but we'll have some carbon disulfide lying around after. B is kind of an interesting question. It says, now, how many moles of the excess reactant remain? So I want to know how many moles of carbon sulfide are going to be left over after the reaction. Okay, so I already know that oxygen is going to fully react. It's my limiting reactant. So I'm going to solve for that. And I'm going to solve to see how much carbon disulfide is going to react with it. So using the ratio between them, 3 moles of oxygen react with 1 mole of carbon disulfide, and I get an answer of 0.33 moles of carbon disulfide. Now we have to remember what we're solving. That is not the amount of excess reagent. That is the amount that will react with 1 mole of oxygen. So I solve to find how much carbon disulfide do I need to react with this oxygen, and based on my ratio of 1 to 3, if I have 1 mole of oxygen, I need 0.33 moles of carbon disulfide. So how much excess remain? Well, it says I'm starting with 1. So 1.00 moles of carbon disulfide minus 0.33 moles of carbon disulfide. Well, the amount that's excess is the 0.66 moles of carbon disulfide. Okay. How many moles of each product are formed? Well, we already solved that for carbon dioxide, right? We found that we are actually going to make the 0.33 moles of carbon dioxide. So we solved that. You can do the same for sulfur dioxide if you are so interested, and it probably would be good practice. So what I'm going to turn and do, though, is I'm going to do number 2, because now we actually have, in a reaction, this would be a great test question. You know, I'm going back and forth between the multiple choice standards-based tests and doing just a question like this for our final exam for the chapter. It's just saying, here's your reaction, tell me everything about it. So we have metallic magnesium, because that would be so much fun, wouldn't it? Metallic magnesium reacts with steam. What is steam? So I have to write the balanced equation first. Reacts with steam. I think that's water is what they want us to produce. That means put an arrow. Magnesium hydroxide and hydrogen gas. So you see the importance of naming. All those little pieces that we did now get so important, because we can't solve a limiting reactant problem if we don't know what hydroxide is. Hydroxide is OH, -1. Magnesium has a positive 2 charge. Magnesium is positive 2. Hydroxide is OH -1. Cross the charges. Magnesium hydroxide MgOH 2. And if you're still struggling on names, you got to go back and start memorizing those polyatomic names. It's going to be essential. It is essential. It already is. So balancing this equation, 2 hydrogens to 4 hydrogens. I need to put it 2 here. Now we have a balanced equation. So how to write the formula, how to balance it. Oh man, everything we've done this chapter. What a great test type question. So it says we have 16.2 grams of magnesium, and it says they're heated with 12.0 grams of water. Okay, so I have my 2 reactants. I'm writing them down. What is the limiting reagent? Okay, I am going to solve it, and I know books and other things are going to have you solve this differently. I'm going to solve these both for a common product, and it doesn't matter which one. I'm going to solve them both to see how much hydrogen gas they produce. So my first step is just like we did before. If they give you a mass, we can't compare things on masses. We have to first change them into moles. So 24.31 grams of magnesium, and this from the periodic table, the molar mass, is 1 mole of magnesium. So I have that into moles. Now, why don't I do, on the bottom, I'll do the water. I'll do water at the same time. Water is 18.02 grams of H2O. That's 1 mole of H2O. Okay. Now what do? So I have my reactants in moles. Now, just like we were doing with molar ratios not too terribly long ago, now, and what we did in the previous problem, we're going to look at the ratios that are going to react. So 1 magnesium is going to produce 1 hydrogen. So that's my ratio. I'm going to throw that in. So 1 mole of Mg makes 1 mole of H2. That is the ratio from the balanced ratio. So I just rewrote this here to make it a little bit cleaner. I don't know if that helps. So here is our ratio. 1 of those to 1 of those. So I have that. I'm going to do the same thing for the water now. Water to hydrogen. So it says 2 moles of water. And again, this is the balanced ratio, is 1 mole of hydrogen. Okay, so we've done that. We have them both into our molar amounts of hydrogen. I want to go one step further to have a mass. Now, I could stop there and compare the mole amounts. My problem's going to ask for grams of each product later anyway, so I might as well just solve them both for grams. So 1 mole of H2 is 2.02 grams. And down here, the same thing, because we're solving them both for hydrogen. So up here, I get 1.3 grams of hydrogen. Actually, 1.3, but we'll cut it off. And down on the bottom, I have 12 times 2. That's 24 divided by 18. Divided by 2, I get 0.6 grams of hydrogen. Okay, so now this gets to be very important. We have to look at what these numbers mean. So if I start with 16 grams of magnesium and 12 grams of water, this is telling me that I could produce 1.3 grams of hydrogen or 0.6. Well, we always want to pick the smallest amount. So we can't make more than what our limiting reactant will allow for. So our limiting reactant is whichever produces least. So this is limiting. So I've identified my limiting reagent. I've identified my excess reagent. This is an excess. And I've identified how much hydrogen I'm actually going to produce. So I've identified my limiting reagent, my excess reagent, and how much I'll actually produce, or what I would call my theoretical yield. Theoretical yield. Okay, I have that down. So that would be my theoretical yield. This number we want to ignore. If they're telling you you'll produce more, that's not true. You can't, because we don't have enough water. Now let's see if we can answer the second part. So we answered A. B says, how many moles of excess reagent are left? Again, how I'm going to do this is I'm going to take my limiting reagent now because I know that value is correct. So I know that I have 12 grams of water, and that's my limiting reagent. I'm going to convert it into moles so I can compare it to something. 18 grams, sorry, I'm rounding a little bit, is 1 mole of water. Now, I'm going to pick the molar ratio that relates these two things. How much magnesium is going to react with that water? Well, I know if I have 2 of these, 2 waters are going to react with every 1 magnesium. So that is my next step in my equation. So 2 moles of H2O react with 1 mole of magnesium. So I have that. Last step, convert this into a mass. 1 mole of magnesium is 24.305, 24.3 grams of magnesium. Solve. I get an answer of 8.1 grams of magnesium. Now remember what this is, because this was my limiting reactant, and I solved it for magnesium. This is the amount of magnesium that will react. So will react. So I haven't answered my question yet, because it wants to know how much of the excess reagent is left. Well, if I started with 16.2, right, and I know 8.1 will react, well, 16.2, which is what I started with, which was excess, minus the 8.1 that will react, I have 8.1 grams of magnesium left. Excess. Left over after the reaction. Nice. So I solved that. That says how many grams of each product are formed. Well, I already solved the hydrogen. You could do the same thing using the water amount and solve for my other product, my magnesium hydroxide as well. So these can kind of be fun, hey? Maybe not. I like them, though. They feel like we're doing some real chemistry. I'm going to do one more with you, and maybe we'll do some extras in a part 2 podcast, but I won't keep you much longer. I'm just going to do number 3. What is the limiting reactant when we have 19.9 grams of copper oxide are exposed to 2.2 grams of hydrogen? According to the reaction, they give us the reaction, they make it easy. How many grams of copper are produced? Okay, no problem when you make it that easy. I'm going to put this up in the corner so I can refer to it, but it's not going to block me too much. I have 19.9 grams of copper, and on the other side, I have 2.02 grams of hydrogen. Now, it's asking me how much copper, I'm sorry, this is copper oxide. That's an important difference. It's asking me how much copper is produced, so I'm going to convert these both to copper. So I don't have to solve the limiting reagent in one and the amount of copper produced in the other. So I'm going to solve this just once. So this is easy. 2.2 grams of hydrogen. I can convert this into moles of hydrogen fairly easily. Now, though, I have to look at the molar ratio. So hydrogen to copper, that's 1 to 1. So this is we also want to check if our equations are balanced. This one is balanced. Gives me 1 mole of copper. Last step, take it out to a mass. 1 mole of copper will produce 63.45 grams of copper. So that's, again, the molar mass from the periodic table. Same thing here. Now, we have to find the molar mass of copper oxide, so we'll just have to add it up here quick. And it's 79.54 grams of copper. If I add up 63 plus 16, here's what we get. Now, the ratio between copper oxide and our copper, hopefully you can see that, is 1 to 1. So 1 mole of copper oxide, 1 mole of copper. Now, again, same as we did here, we have to convert it out to a mass of copper, 63.55 grams of copper. So if we run these both through, we'll get some numbers. We'll be able to figure out what our limiting reactant is, what our excess reagent is, and the amount of copper we'll produce in this reaction. Okay, in the first one, I'll produce 15.89 grams of copper. In the second one, I'll produce 63.55 grams of copper. So what this is telling me, this is not possible. We also picked the little smaller amount. So that means this, let me label all of these. This is theoretical. I'll produce this as my theoretical amount. This is my limiting reagent. And this is an excess. So how much excess we don't really know because we haven't solved that but at least I've identified what's my limiting reagent, whatever produces less, what's my theoretical yield, and what is excess. So last thing that you might have to do on these is, it might often ask for percent yield, and we've done these a little bit. Again, your theoretical yield is what actually could be produced based upon our calculations from the limiting reactant. And actual yield is what would be performed, what we would make in lab. Now, a lot of times when we've already done these calculations, we'll calculate the percent yield, which is that actual divided by what our theoretical would be times 100, and that's going to give us a percent yield. We will use that often here when we're doing these limiting reactant types of calculations.